Welcome back to another lecture of Statistics 479 Time Series Analysis. Today, we're going to be doing what we did in the last lecture, but we're going to be doing it in R, so it's going to be a whole lot more fun. So in today's lecture, what we'll be doing is testing for autocorrelations and testing for stationarity of our time series process. And we get to look at real data, which is a lot of fun, because we're often interested in whether or not there's going to be significant autocorrelations at various lags. We also want to know if we have a stationary process, because that's going to allow us to actually do statistics. So how do we test for that? Well, let's go find out. Welcome back to another lecture of Statistics 479 Time Series Analysis. We're going to do a part 2 to the previous lecture, because in the previous lecture we spent the entire time looking at all of these different statistical tests, mainly for 2 topics, being autocorrelation testing and testing for stationarity, or the lack of stationarity. So what we're going to do is jump right into RStudio from the start and try to see exactly how this works in practice, and try to take a little break from some of the heavy equations and actually see how to do work with actual time series data. So let's take a look at some of these packages. All right, so here we are in RStudio, and the first thing I want to do is generate, let's say 500 time points of WN, which is going to be our white noise. All right, that's going to be the basis. So what I want to do is I want to generate some sample time series, some simulated, I should say, time series data, so that we can work with it and we kind of know what the answer is supposed to be before we go forward. So once again, I can also create an AR1, that is an autoregressive order 1 process, by picking a value like, let's say, 0.7 as my coefficient, and I need to tell R that the method that I'm using is recursive. Cursive, there it is. Excellent. So these would be 2 things. We could also create a more complex model, and I'm going to pray that if I just arbitrarily choose some values here, that I don't accidentally create something that is either non-stationary or explosive. If I make the value small enough, presumably it should be okay, but we'll double check by just looking at the simulated data to see what happens. So let's look at AR4 and make sure it doesn't just blow up. Okay, no, that looks pretty good. It didn't blow up. Because if I pick the wrong, or if I choose certain values for this filter here, I can very easily cause the entire thing to blow up and fail. Okay, so now that we have these 3 series, we have to think about, well, a couple things we want to do is we want to test for autocorrelations. We also want to test for whether or not these series are stationary. And lastly, we also need to know about how to fit time series models to our data. So we didn't actually discuss this yet in the course. This is something that we'll be doing later in the course when we talk about how to actually estimate the coefficients for time series data, right? Because this is statistics, and eventually we actually want to fit coefficients to that crazy noise on the right-hand side here. So what we want to do, well, there are multiple functions that we can use. We can use the AR function, and this just fits an AR model, an autoregressive model, to time series data. So if I give it white noise, for example, it says, okay, I basically have an order 0, so it kind of identifies that, yeah, this looks like white noise. And because I have 500 data points and it's simulated data, it should do a pretty good job at guessing the coefficients. Here I put 0.7, it came up with 0.7108. So it did a pretty good job at estimating the correct coefficient. And AR4, let's see how well that does. Yeah, it actually did a pretty good job. It got, this is supposed to be 0.7, this is supposed to be minus 4, 0.4 that is. This is supposed to be plus 0.2, and this is supposed to be minus 0.1. So it did a pretty good job at getting most of those coefficients. And in all cases, it's getting the fact that the variance is 1, because the white noise process I started with has a standard both, I guess, a variant and a standard deviation of 1, because I didn't change it from the default value. So that's one way, but another way that we can actually fit models, more complex ARIMA models, to a data set is to use the ARIMA function. And the ARIMA function here is going to want us to give it some data like white noise, and then we have to specify an order. So the AR function there decides what the order of the autoregressive process is. The ARIMA function, you have to tell it exactly what you want. So I could say fit an AR2 MA1 ARMA model to this white noise process, and it does that. It's not a good one, but it does it, right? And if we spend some more time looking at these coefficients, using things like model selection with AIC, we could try to figure out what the best model is for our data. We're not going to go into that right now. I'm really just introducing these functions because eventually we'll want to look at the residuals after fitting a model to our data. Actually, we could even do that with the prescription data, so maybe we'll do that in the real data sense too. But anyway, and there's actually other functions like auto-ARIMA, which will determine the order for you, as well as look at seasonal models. Though actually, now that I look at it, yeah, this one does seasonal models too, so we're good there. But what we really want to do is look at some of these statistical tests that we talked about in the last lecture. The first one is box dot test. And box test, or the box-Pierce versus the Ljung-Box tests, or Ljung, yeah, I can never get that right. Box tests. Regardless, this box dot test function is going to give you the ability to run either of these two tests like we talked about in the last lecture. And remember, the point of these is to look for autocorrelations at a specific or up to a specific lag. So remember what we're going to do. We're going to say the null hypothesis is that there's no autocorrelations at, the first whatever H lags that I choose, and the alternative is at least one of those autocorrelations is non-zero. So if I put the white noise time series into this, then let's say, well, it just defaults to lag 1, but I'm going to write it in anyway. Lag 1, and we'll do the box Pierce method. Recall that box Pierce is just the sum of the squared estimated autocorrelations, and the box Ljung test is Ljung test is going to be the sum of the squared autocorrelations with different weights based on the total sample size n and the index j. So it's a slightly different thing. Both of these are supposed to be chi-squared. The claim is that the latter of the two tests is better in the sense that it better gets the moments of the null distribution that you would want, at least in the null setting. Regardless, when I hit enter, we run this test, and what do we get? An extremely insignificant p-value, just as we would expect, because there is no autocorrelation at lag 1. And I can bring this up to 10 if I wanted, and I still get a insignificant p-value, and so on. I probably shouldn't make it really big, but we can do it big anyway. And yeah, now you're getting a slightly smaller p-value, but you probably shouldn't put 50 in there and either. It would actually be really interesting to run a simulation test to see how this performs, especially when you give it very large lags. Remember, this is all based on estimated autocorrelations, and the bigger the lag is, the harder it is to estimate accurately that autocorrelation. And I do have 500 data points, but 50 is starting to get kind of big in that sense. It's 10% of the way through the time series. So again, typically you wouldn't go out that big, but it's just something to notice. In contrast, if I give it an AR1 process, then wow, we get an extremely significant p-value, as we certainly should. And even if I increase the lag to 10, well, we still get an extremely significant p-value, because remember what we're doing is we're looking at the sum of the first first 10 lags. So as long as one of them is significant, then we have a very significant p-value here. Of course, I can change this to the other test by changing the type. It's not going to make a huge difference. The test statistic, the value of x squared, the test statistic has increased slightly. So yeah, in some sense, it's, I guess, slightly more significant, but it's already absurdly significant. So at that point, it's like, who really cares? But now that I think about it, maybe what we should do is try to come up with a little bit of a harder test for it. So I'm going to call this AR1A, and we're going to make this just 0.05. So now I'm going to make it a lot harder to detect it, because it is technically an AR1 process, but the coefficient is very small. So is it too small to detect? I don't know. We'll have to find out. Secondly, I can create an AR2 process that doesn't have an AR1 coefficient in it. So remember, an AR2 would have a phi1 and a phi2. So what I'm going to do is I'm going to set phi1 to 0 and just leave phi2 there. And that's what I'm doing here by putting a 0 first. So there's two things going on here. The first is, let's see if the box Pierce test can actually detect that there is a non-zero autocorrelation at lag 1. And no, it missed it. Yeah, sadly, it did not detect it. The value was too small. Let's see if the other one, the Ljung-Box test, can do it. And nope, it looks like it gave just about the exact same test statistic size. So in this case, it was not able to detect it because I made that coefficient here too small to be detectable, even with 500 data points. Maybe if I created 5,000 or 50,000, we might have enough data to detect this, but at 500, we don't have enough. Now, the reason why I created this AR2 is that, remember, there is no autocorrelation at lag 1. So I did this on purpose to point out that if you did this test and it defaults to lag 1, then you'd say, well, that's not significant at all. I got a 0.24. So maybe there is no autocorrelation here. But if I switch it to lag 2, now suddenly I get an extremely significant p-value. And we can see that if we look at the autocorrelation, the estimated autocorrelation function for this AR2. Because if we do that, see, we see nothing at lag 1. We see this tiny little like demi spike here, but then at lag 2, we see quite a big spike. And notice for future reference that this spike looks to be right around the value of 0.7, which, happens to be the exact value that I set the coefficient to be. So yeah, that might be relevant later in the course. Similarly, if I look at the AR1 process I generated first, it looks like the exact same autocorrelation, but without that alternating sort of zero significant, zero significant, zero significant thing going on. And also, if I look at the AR1 here with my extremely small coefficient of 0.05, yeah, it falls below this noise floor. So we would need to probably be above that noise floor if we hope to detect any significant autocorrelations. And as far as we can tell from this data, this process here is going to look just the same as white noise does, at least given 500 data points. Again, maybe if we had more, we'd be able to do a better job detecting that significant autocorrelation. All right, so that's just the box test function. Again, and there's one other thing that I did want to mention, though, about the box test function before we stop. And that is, remember that it is often applied to, as it says here, it's often applied to the residuals after fitting an ARMA PQ model to the data. And then what we need to do is subtract the number of parameters fitted from the degrees of freedom, which comes into this fit df function. So remember, if we're actually fitting a model first, we need to subtract the number of parameters from our degrees of freedom. Now, this can all be made more properly rigorous, but roughly is the same thing we would do in linear regression. If you think about it, when you have degrees of freedom, you're typically subtracting them for everything that you estimate in your model. So let's try that with our AR4. Because remember, I generated this AR4 process at the start. And it looks something like that. So again, all these processes look kind of noisy. I mean, that's what they are, right? They should be stationary processes if I did everything correctly. But what we can do is we can actually fit a model to this using the ARIMA function. So what I want to try to do is I'll fit a good model and I'll fit a bad model. So we'll call this model.good. And I'm going to fit the correct model. Again, a priori, I wouldn't actually know what the right order is to fit. I would have to do some model selection. But in this case, because I simulated this data, I know it's an AR4 process. So that's exactly what I'm going to fit. And if I look at my model.good, well, yeah, it did a pretty good job at estimating all of the terms. Now, what if I fit a we'll call it model.bad, and I'm going to fit an AR1 model, which is not the correct model to fit to this data set. So first, let's just look at it. Well, for one, the AIC is a little bit bigger. So again, if we actually were trying to do model selection, we might come back here and say, this model looks better. But let's forget that for a moment and just look at the residuals. Because remember, this box test is very much interested in the residuals for our our ARMA process. So if I were to just take the AR4 and then say lag is equal to, I don't know, 1 or even 4, and if I said fit df is equal to 0, because this is just the original process, not the residuals of the fitted model, then yeah, I get my extremely significant p-value. But let's see what happens if we try this on the residuals of model. Did I fit m? Oh yeah, model.good. That's what I wanted. And remember, what I need to do is I need to subtract 4, which means I can't do lag 4. So presumably this is going to give me an error. Nope, it's going to do something with 0 degrees of freedom, which actually really baffles me because I have no idea why. That's actually fascinating that R will do that with 0 degrees of freedom. I didn't think that would work. Let's try 5 just to see what happens. No, there we go. So it's not happy with -1 degrees of freedom, but for some reason, the chi-squared, that's actually really funny. We're going to do a quick diversion live on the air. Yeah, so apparently non-negative. That's amazing. So why in the world can the degrees of freedom be 0? I guess that would just be a degenerate distribution. If the degrees of freedom were 0, then presumably it would just be a spike at 0. That's actually really peculiar. Regardless, you don't want to do that if you're fitting a model like this. So what you'd want to do is you'd want to increase the lag. It just has to be bigger than 4 so that you have at least 1 degree of freedom. And now you get an insignificant p-value, as you would expect. Because remember, what I did was I took my AR4 process, I fit the exact AR4 model to it, and then I just extracted the residuals. In that case, the residuals should look like they are uncorrelated, and sure enough, they do. Whereas if I accidentally didn't do it right, I'd either get an error if I had negative degrees of freedom, or if I got 0 degrees of freedom, I'd actually get a really significant p-value, which is completely erroneous, which means that you got to really be careful when you plug things into R, because if you're not paying attention, you would look at this and say, look, that looks really significant. I guess there's some significant autocorrelations, but no, it's just because 0 degrees of freedom, like why? Anyway, before I rant about that, let's see what happens if we do the same thing to model.bad. I don't actually know what's going to happen here. It might actually be fine. Nope, it's not fine. Excellent. That's what I was kind of hoping for. So yeah, if you notice that compared to the value of the test statistic now here is extremely large, it's close to 40 for a chi-squared with 1 degree of freedom, which is absurdly a significant value, compared to the test statistic here, which is 0.033, which is incredibly small. So this is where you can kind of see the where this test could be useful. You fit an ARMA model, in this case ARIMA, but we didn't put a differencing term in here. So we fit an ARMA model to our process, to our data. Then we look at the residuals, and we can use the box test to tell us, are there any significant autocorrelations? And sure enough, it says, yeah, there are, which means we probably didn't fit the right model. And model.bad is the correct way to, I guess, the correct name for that model. We can also just look. So again, the box Pierce test is nice in the sense that it's doing some type of proper statistical test based on a chi-square distribution. But ultimately, you can just stare at the autocorrelation function. And again, it may not be obvious. You look at this and you say, okay, well, this looks like a little spike, but that doesn't look very significant. This spike at lag 2 looks like it is a bit above this blue dashed noise floor. So again, it kind of says, yeah, there might be something here, but it may not be immediately obvious like it would be if you just fit, for example, the AR4 process itself, or you put the AR4 process into this, and then you got some incredibly large spikes. At least this one is incredibly large. So that's really the thought process here, and how you can use the box test and why these tests are useful. And again, the two different methods, whether it's Pierce or Ljung, they're both going to do about the same thing. Just out of curiosity, though, why don't we try the other one just to see what happens if we get a more or less significant statistic. So our statistic in this case is slightly more significant at 40.1 versus 39.7. So yeah, it still doesn't change our results, right? And presumably we'll have a very similar, very small p-value that is basically the same test statistic that I got in both cases, and a very, I should say, large p-value or insignificant p-value. So all right, that's the box test, and that's one tool that we can use to analyze both time series data and the residuals after fitting a time series model to our time series data. See how many times I can say time series in the same sentence. And the next thing we're going to talk about is the Durbin-Watson test, and that one we need to load in a library, which is lm test. And yep, everything's good. It's just giving me some other information about packages it has loaded in. So remember, the Durbin-Watson test, as we talked about last time, is applied to the residuals. And it's looking for the same, it's kind of doing the same thing in the sense it's looking for those correlations, but specifically at lag 1. So let's try it out and see what happens. DW test no dot. Well, first let's look at the documentation. So when we look at the documentation, it actually wants a formula. So what it wants is it wants some type of a regression-like formula. But we can apply this just to a time series without a linear regression if we, give it a null formula, which I'll show you in a second. Otherwise, we just have some other arguments here, which things like specifying alternative hypotheses, which we're going to ignore for the time being. So if I wanted to run this on my white noise process, I can use the formula tilde1, which basically says fit an intercept. It's a regression, basically a linear model, which is just an intercept term. So it'll shift it up or down to make sure it's mean 0, but otherwise it's not doing anything. And what I get is, a very insignificant p-value. And it says, the alternative hypothesis here is that the true autocorrelation is greater than 0. So what I could do, maybe I should change this alternative to be, it should be two-sided. It doesn't have to be. It could be, I think you can have it as greater, two-sided, or less. So you can strictly look for positive autocorrelations, negative autocorrelations, or run a two-sided test. Either way, this is extremely insignificant. Remember, as we talked about last time, the most insignificant value for the test statistic is 2. Again, this is a little bit weird because so many test statistics, 0 is insignificant and big is significant. In this case, 2 is insignificant and getting close to 0 or 4 will be very significant. So for example, if I put in my AR1 process here, then yeah, it turns out that I get a value pretty close to 0, and sure enough, it's very significant. Now, the nice thing about this is that I can actually put in a formula here. I don't have a formula to put in at the moment, but we will maybe, yeah, actually, why don't we do that now? Rather than go back later, I was going to say what we can do is we can load in some time series libraries, like our TSA library. We can load in our T-series, which we'll need later anyway. And I believe that we should have our prescript data, which we looked at in the previous lectures, that I occasionally write precip, which is the wrong data set. So there's our prescription drug data. So again, if I come in here, then what I should be able to do is fit well, first of all, if I just type in prescript, I should get something that's absurdly significant. It's not even stationary, so that's no good. It's increasing. But we'll see if this works. I think I should be able to tell it to do a regression based on the time, which is really just fit a line to this data, a straight line. So it's going to remove this positive trend as we go through the years, the increase in prescription drug, or the increase in the cost of prescription drugs. Okay, so that's still really significant. So what it's telling me is that even after I fit a linear model to this, I still have a very significant autocorrelation at lag 1. And we actually can look at that in the ACF function by, this is going to be terrible coding, by the way, but I'm going to nest everything because I don't really feel like writing it on separate lines. So we want the ACF of the residuals of a linear model that is prescript time prescript. Okay, that looks nasty, but let's just do it. And yeah, sure enough, if you run this, you do get kind of a spike here. Again, it's not that high above the noise floor, but it's high enough that the Durbin-Watson test says, yep, that definitely looks to be very significant autocorrelation in the errors, in the residuals. Therefore, we're going to reject our null. And this was going, I think, a two-sided test, but either way, yeah, it's still a very small test statistic there. Okay, so we have that. I guess while we're at it, we could try using the box test on this just to see what happens. It shouldn't be that much different. Remember, Durbin-Watson is looking specifically for an autocorrelation at lag 1, whereas the box test we can extend to other lags. And box test is looking at the estimated autocorrelations, whereas the Durbin-Watson is looking at the residuals of the fitted or the time series data itself. Anyway, let's try I don't know, lag 5. Yep, so that's also very significant. I guess technically we should probably note that we fit 2 parameters here, a slope and an intercept. So I should probably remove those, but yeah, it's still going to be really significant. So that's not going to change anything. All right, so that was Durbin-Watson. Again, it's not much different in practice than what we did. Actually, there's one more thing I do want to check though with Durbin-Watson while we're doing this, is that what would happen if we looked at that AR2 process. I believe we should get an insignificant p-value because it's only looking at the autocorrelation at lag 1. So let's see if that's true. It is true. We get an insignificant p-value because at lag 1, nothing is happening interesting with this process, but at lag 2, we have something very significant happening. So again, you have to be a little careful when you're using a test like this. It's only looking for autocorrelations at lag 1. Though granted, typically you wouldn't see a time series like this AR2 that I generated, because this AR2 is basically like interweaving 2 time series together that are AR1s, and we're just observing them alternating and alternating. So again, it doesn't, I don't know. I mean, maybe there are cases in practice where it does show up. I don't have any off the top of my head, but that doesn't mean they don't exist by any means. All right. Now we'll move on to the next one, which is this Bruch-Godfrey test. I'm just assuming that's how you pronounce it. Anyway, let's look at the BG test. So the BG test, again, is higher order serial correlation. When you see them say serial correlation, that's what it's autocorrelation. It's a synonym, at least. I don't believe there's any real difference there. But yeah, in our text, we use autocorrelation. In other texts, you'll see them say serial correlation. But the approach is the same thing as the DW, the Durbin-Watson test, but now there's an order here that we can work with. So I can change the order, and that will give me, well, the ability to test for autocorrelations beyond lag 1. Furthermore, we also have a chi-squared and an f-test version. Remember, these are 2 different ways to approach this. The chi-squared is asymptotic. It looks at the r-squared value, where the f is just the classic f statistic. So let's just see how that works. I think we kind of know all these tests ultimately kind of do the same thing. So there's not a great reason why one might be necessarily better than the other. But it's worth knowing what they all do. It's kind of like when you do goodness of fit tests. You've got like Kolmogorov-Smirnov, you've got Anderson-Darling, you've got Shapiro-Wilks, you've got Kramer-von Mises. They all do the same thing. Mathematically, yeah, they're a little bit different, but they're usually going to agree. And similarly here, at least with this data, these data sets, they all kind of agree. Anyway, yeah, let's say if we try this, but let's just do order like 6 because we can. And yep, we don't see anything significant with our white noise as expected. So even up to order 6, we see nothing significant here. And this is also, let me see, where are we? Yeah, we have type is chi-squared. I could change type to be f. And we get a completely different test statistic here, but we similarly get a very insignificant and oddly similar p-value. Though the test statistic does change because the distribution we're looking at also changes from chi-squared to f, of course. Now, if we have our AR1, let's see what that does. Well, that is, yeah, really, really significant as we would expect. And probably even if I increase the order unnecessarily, it would still be really significant. And even if I presumably changed the type to an F test, it should also still be significant. Yep. So that's all what we would expect. The nice thing about this method is that if I switch to that AR2 at order 1 with, let's say, a chi-square, the standard chi-square test, well, it's not significant, just like the DW test before it. But the nice thing about this one is I can switch to order 2, and now I get something that's super significant at order 2. So that's, again, why this BG test is a little bit nicer than the Durbin-Watson, because I can actually go beyond order 1. And yeah, otherwise, I don't think there's anything that exciting to report about this. We could go back and look at that prescription data. Oh, that's something interesting to note. This one doesn't give you the option of doing a one-sided or two-sided test. I think it's just two-sided because we're looking at just the R² value in terms of a chi-squared distribution. So in this case, the BG test does not give us the ability to do it. It shouldn't give us the ability to do a one-sided test. It would just be a two-sided test because it's the sum of a bunch of squared things. Whereas with the DW test, we can look to see if we're getting above 2 or below 2, and if it's one-sided. So there's one reason why you might prefer the DW test. If you're particularly interested in something like a one-sided test, like I only care about positive autocorrelation, then you can get more statistical power for detecting that if you use a one-sided test, which is why somebody might want to use a one-sided test. Otherwise, there's nothing much going on different. And in this case, all the examples I have are so significant that there's nothing too exciting there to take note of. Regardless, the BG test still gives me a very significant p-value here. And presumably if I increase the order even up to like 6 or something, I still get a significant p-value. So, nothing in some sense interesting. I mean, the results, of course, interesting, but it's just telling us that fitting a line to that prescription data is not telling the whole story. There's more stuff going on there, which of course is, in a sense, kind of obvious when you, if you plot the, I don't want to delete that. If you were to plot the residuals, it's kind of blatantly obvious that there is something going on there, right? If I just said residuals and then said plot these things, well then, I guess maybe I should give it type lines. So when you look at this and you say, okay, that does not look like a nice uncorrelated residuals. There's definitely a lot of stuff going on here that needs to be dealt with. So it's not surprising that we're getting these incredibly significant p-values, but it is still nice to have a good hypothesis test. So the next thing we're going to look at is the unit root tests for stationarity. This gets into the idea of the augmented Dickey-Fuller test, which I believe is in the T-series package, which I already loaded in, so we're all good to go. So here we have the ADF, or the augmented Dickey-Fuller test. Again, we have sort of different arguments. The main one is we plug in the data. It can determine the lag that we want for testing. Again, remember, this is the augmented Dickey-Fuller test, not just the regular Dickey-Fuller. Regular Dickey-Fuller was just for the AR1 model. Augmented Dickey-Fuller goes all the way up to ARP for whatever you want P to be. It defaults to choosing actually a fairly large value in the sense that it takes the length of the data. For some reason, it subtracts 1 and then takes a cube root. I'm not sure why the programmers decided that's the best default value. I guess because it corresponds to the suggested upper bound on the rate at which the number of lags k should be made to grow with the sample size for a general ARMA PQ setup. So I guess that's the reason why. Luckily they actually tell you. Sometimes they don't actually tell you. Anyway, now that we have this, let's see what it does. So if I plug in my white noise model, again, what we're doing is we're testing for stationarity, whether or not our distribution is stationary, but that is the alternative hypothesis. The null is non-stationary, that a unit root exists. Because remember, in statistics, typically our null hypothesis, we want it to be that some parameter takes a specific value, and the alternative is usually it doesn't take that value. So in this case, we're saying we have precisely a unit root that is, one of the roots is 1, I guess is a unit, or it's not a unit, which is our alternative. So when I run this, what I get is, well, a couple things. First, I get it tells me what the lag order is, which is, I guess, the cube root of 500 or something like that, which, is that right? Yeah, I guess maybe it is. Anyway, what we get is a p-value of 0.01 and a warning message saying, you know what, that p-value is probably smaller than what was printed. So then it makes you wonder, well, like what is going on there? It's because remember that the distribution that we compare this to is not it's not necessarily easy to work out. You can fight your way through the source code and you can see some amazingly amusing stuff going on here. Because if you read about the Dickey-Fuller test, they don't usually tell you what the distribution you're comparing it to. But if you fight your way through the source code, you might notice something interesting, which is that somewhere along here, they start to define a table. And then they get these p-values here. And I believe somewhere in here, we actually interpolate. We do a linear approximation within this table, table P, for our, I guess, test statistic value. So what we're actually doing is we're taking these tables and we're interpolating, and the smallest value you get here is 0.01. Hence, presumably, if you could, I guess, try to figure out what this distribution looks like as you go below 0.01, but the coders here did not do that. I'm not very familiar with what this distribution actually looks like. It's just quite amusing to me that when you look at the source code, one of the best things about R is you can always look at the source code. And what's great about looking at the source code is you can see this crazy interpolation thing, linear interpolation using the approx function that they're doing in here. And then, of course, spitting out warnings saying, yeah, you probably have an even smaller p-value. We just can't compute it. So, you know, just take note of that. But while we're at this, what we could do is we could shrink our data size just to see what happens. Because 500 white noise observations, yeah, that's pretty significant. What if we did 50? Well, we still get a significant p-value now, but it's, well, okay, I say significant. We get a p-value less than 0.05. If you like that, then you can call this significant. Otherwise, yeah, don't. But it's still a fairly small p-value, which seems to be indicating that we might be able to reject the null hypothesis that a unit root exists, hence accept the alternative hypothesis that our data is in fact stationary. Yeah, so that's something to take note. And if we reduce this further down to like 20, we don't have a significant p-value anymore. And that's quite interesting. What it's telling us is saying, you know what? I don't know if there is a significant root here or not. I mean, we don't have enough evidence to reject the null hypothesis that there's a unit root, to reject the null hypothesis that our time series is non-stationary. I want to see what happens if we can't do lag is equal to 1. Oh, it's k, that's why. Yeah, if I change this to lag 1 or lag order 1, then I get back my, let's say, much more significant p-value. So in this case, actually choosing the lag order can kind of save you a little bit and still tell you, nope, this actually looks like it could be significant, meaning that there is no unit root. Again, this is a little bit confusing because it kind of is the opposite of what you would think you'd want to do in statistics. You think you'd want to test with the null hypothesis that your distribution is stationary, but in fact, in this case, our alternative is that it is stationary. Okay, so what else can we do with this? Well, we can test our AR4. What in the world did I do? Oh, no, that just gave me the usual standard warning that, yeah, we have a really small p-value. And even if I let it go up to lag order 7, it still says, yep, we have a really small p-value. Now, what I can do to show you what happens in the other case is that I can use the cumsum function, which cumulatively sums a vector of numbers. In this case, if I take white noise and I start adding white noise to itself, I get a random walk, right? This is like the cheap way to just create a random walk in R, generate a bunch of normal IID normal random variables using R norm, and then just cumulatively sum them up. And what we should get is something that's, extremely not significant, because this is white noise, or this is not white noise, this is a random walk now. And the random walk is our sort of standard non-stationary process that we like to use as an example. In this case, it defaulted the lag to be 1. If I let the lag grow to 7, which is the I guess the default for this, then we still get more or less the same idea, a very insignificant p-value, which is kind of hinting at, there's probably a unit root somewhere in here. And sure enough, if I use the AR function to try to estimate the parameters, I get a value. It's not 1, it's 0.9924, because the AR function will only estimate for stationary processes. It should be causal, I believe. It should only work for causal stationary processes. So in this case, when it sees this, it says, okay, well, I'm going to pick a number that's less than 1, but it's really close to 1. And sure enough, if we do a statistical test saying, is this any different than 1? It says no. Up to the errors, this is effectively 1, sort of statistically. So that's that. Another interesting thing, though, is to look at is what we can learn about that prescription drug data. Now, I think we did this a little bit in a previous lecture, but let's look at it now that we understand this test a little bit more. Let's look at it and see what happens. So if I take the prescription drug data set and I run the augmented Dickey-Fuller test, it actually says, you know what? It looks stationary. I'm going to reject that null. But you might remember and say to yourself, well, wait a minute. What did that plot look like? That plot looks like this. That's definitely not stationary. It's increasing, right? It can't possibly be stationary because the mean, maybe the autocovariance is, but the mean is certainly not stationary. And that's where you also have to be careful and carefully read the documentation here, because what it does, it doesn't just it doesn't just run the augmented Dickey-Fuller test on the time series X. It first tries to remove a constant and linear trend. So that's another key thing to note, that what it's actually doing is it's fitting a straight line to that data, and then it's kind of, looking at, I guess, the residual process after it does that. So what that means is that in this case, after we were to remove, if we were to remove that linear trend, we would get something that looks stationary, which is nice, because it means if we go back to our, I think I already had it over here in the plots. If we go back to this autocorrelation, we can kind of say, this looks like a stationary process. That is, this thing that I plotted here looks like a stationary process according to the augmented Dickey-Fuller test. Now, there's still a lot of behavior there. There are a lot of significant autocorrelations, but it still gets to be stationary. All right, so we have, I think that's all there really is to say about the augmented Dickey-Fuller test. We have one more test to look at, the Phillips-Perron test, or the PP test in R. So let's look at that. This is also in the time series or T series package. It is kind of effectively looks the same as the augmented Dickey-Fuller test, and presumably it's going to give us a lot of the same results. Now, again, it says the general regression equation incorporates a constant and a linear trend. So in that case, what we're doing is, again, we're removing those that constant and linear trend. So while we're at it, why don't we just try running it on the prescription data. And what do we get? Well, we get a small-ish p-value below the magic 0.05 threshold. Don't always go with the 0.05 threshold. It's just not worth it. You got to kind of think on your feet. But at the very least, the p-value is kind of small, which is hinting that after removing that linear trend, that the residual process looks kind of stationary. Again, not super strong, but it is still getting there. And why don't we try running the same thing on, say, the white noise process, and hopefully we get an extremely insignificant p-value. And sure enough, we do. At 0.9118, we have a very large p-value, which is kind of saying, yep, there is probably a unit root somewhere in this time series data. Now, I think I had a couple other examples that we could try just to see what happens. Well, we could run it on white noise itself. We should definitely see something in. Yeah, in this case, it's giving me the same error saying, you know what? The p-value is probably a lot smaller than that, but we can't actually compute that far, because if we look at the source code again, oh, look, it's doing another table. And I think this also does another approximation. So computing p-values is not an easy thing. So I don't want to knock them for this. I think it's actually quite interesting. And at some point, I'd like to read up myself and understand exactly what the programmer decided they would do while trying to come up with this, because it is quite interesting. And I find computing p-values to be a very interesting subject. Dickey-Fuller type. Anyway, I wonder if the test can be run together somehow. Anyway, what I wanted to do was to try to truncate this and see what happens, because remember before I said that, okay, if we have 500 white noise observations, well, that's definitely significant, but that's very detectable. But what if we start to reduce the number of observations? So at 50, we still get as small of a p-value as this thing will possibly return. And even at 20, we still get an extremely small p-value. So if you recall, I think when we did this test, we now no longer, so augmented Dickey-Fuller does not detect the stationarity of our process with only 20 white noise observations. Meanwhile, Phillips-Perron does still return a very small p-value. So that's quite an interesting difference, where we see now the tests are actually not agreeing with each other. We know what the right answer is. The right answer is Phillips-Perron, which says it is stationary. So again, it's good to try these things out just to see, okay, what can these tests actually tell me? What if I change my data size? What if I know what the right answer is, but I still kind of mess around with it anyway? We can do the same thing with the AR1 data set that I have. Again, this should look very stationary, but maybe if I reduce the amount of data, then suddenly, we're not sure if it's stationary or not anymore, even with the Phillips-Perron test, and presumably also with the augmented Dickey-Fuller test. Yeah. In this case, remember, we have an AR coefficient, an AR1 coefficient of 0.7. It's not close to 1 in the sense that, but it's still large. And that means that if I need more data to detect that there's a difference between that number and 1, so presumably we'd actually need a decent amount of data to detect that. So 100 seems to work. 50 actually gave me a smaller p-value. It's just sort of dumb luck. But yeah, you can kind of see what happens as we go down to 30. Then suddenly we have a p-value slightly above the magic 5% threshold. If we go back to 20, we get something that now looks like a p-value of 50%, which is horrendously not significant. So again, playing with these, I can play with these all day, but playing with these allows you to get a sense of how they work on real data with real time series processes. We can use real data like the prescription drugs, or we can generate our own. By simulating our own, it gives us the ability to kind of understand how these tests work. what kind of data sizes would we expect to need to be able to detect significance or lack thereof in these different tests. And similarly, we now have two different things we can do. We can look for significant autocorrelations. We can also look for unit roots in the autoregressive polynomial. And a unit root means it's not going to be stationary, which is, again, what we discussed in the past lectures. So with all of that, I think we're going to just end this and call it a short lecture. Because after this, what we're going to discuss is we're going to go back and we're going to discuss autocorrelation and something called partial autocorrelation. So actually, why don't we do a little sneak preview of that? Rather than switching over to the notes right now, let's look at what the PACF is. This is a little off script, so we're just going to run with it. But here's the idea. If I have an autoregressive process of order 1, I get a autocorrelation that looks like this. As I noted before, and what I should do is use the one from the stats package because I like it better. Okay, so again, the autocorrelation function at lag 0, it is, well, it's going to be 0. At lag 0, it's going to be 1 because it's always going to be correlated perfectly with itself. At lag 2, again, I noted, I said, hey, we're actually getting a value of 0.7, which is kind of what we set that value to be. So that's kind of interesting. But if I were to look at, say, the AR4 process, it's a little bit less obvious, like what's going on here. I have a spike here at lag 1, but then I have some kind of noise after that. So then you think, well, what can that tell us? Well, another thing we can look at is the PACF, which is something called the partial autocorrelation function. I didn't tell you what that is. We're going to talk about it in the next lecture, but let's look at a plot of it anyway. And if we look at a plot of it, we see at lag 1, so this one doesn't have a 0. At lag 1, we see a big spike at 7 and then nothing after that. So in contrast, at 0.7, I should say a big spike of 0.7. Whereas here we see this steady decrease. And that's actually quite interesting because that's going to say, hey, what it's actually telling us is that we have an AR1 process here by having a big spike at lag 1. When we switch to our AR4, well, now we get a spike at 1, we get a spike at 2, and then we kind of lose it. So it's not as obvious that this should be a 4th order AR process, but we can kind of see what's going on. Oh, sorry, that's the ACF. What I wanted was the PACF. And there we have something that I was hoping for, which is we have a lag 1 big spike, 2 big spike, 3 not so much, but 4 we have a big spike, and then everything else doesn't look that exciting. So the spoiler for the next lecture is that the PACF function will be able to tell us something about the order of our autoregressive process. So what we can see here is that for our AR4, the last significant spike is around lag 4. And if I switch to this AR2, I see a really big significant spike at lag 2. And I don't see anything else here after that that looks very significant at all. So again, that's very hand wavy. I didn't even define this, so I do apologize for that. But the ACF and the PACF can tell us a lot about whether we have an AR or an MA or some type of more complex ARMA model that we're working with. It's quite a neat topic. It's a little complicated, but the pictures are really nice. So we will definitely be looking at that in the next lecture.